So just to remind you, there's homework. Our first homework was for this Thursday, correct? The 10th. And the problems are 113, 115, 120, 121, and then I had 125, and there you're going to make a bar graph in Minitab. 131, the stem plot's already there for you. You just answer some questions about the stem plot and reading the data, reading the stem plot. And then 135 required a histogram. And when you read 135, it asks you to write a brief description of the distribution. It doesn't tell you exactly what you should include in that brief description. What you should include is the shape, the center, the spread. It does ask you about outliers, and it appears there are a couple, three, I think. Okay. So what I'm trying to do for you is that problem is so far at the end of the chapter is eventually they don't tell you exactly what you want to do. You're supposed to know by the time we get to those problems that if somebody asks you to write a brief description of the distribution, describe, interpret the histogram, you're supposed to tell me about the shape, the center, the spread, and do you see any possible outliers? So I'm just reminding you what you're supposed to tell me at that point. Now, where we left off last Thursday is I'm pretty sure the last thing I did was we were looking at those travel times for New York and North Carolina. We made a box plot that shows you the 5-number summary. Does that sound right? Okay. And we're going to come back to that box plot in a little bit, but one of the things I would like to mention to you about a box plot is a box plot, and I'm going to give you, usually will give you an idea about the shape of the distribution. In other words, it'll give you an idea about the shape of your histogram. Okay? So here's the way I think about it. If it's roughly symmetric, now this goes both ways. All right? If the shape is roughly symmetric, if I'm talking about the distribution and it's roughly symmetric, your histogram is roughly symmetric, or your stem plot, what I would expect to see in your box plot is that the first, Q1, Q3, so those are your two core, the first and third quartiles, right? That's the two quartiles we talked about, are equally distant from translation. When you're looking at your box plot, if the median's about in the middle of the first and third quartile in the box, we're expecting to see a roughly symmetric distribution there. Now look, here's a reason for this. I'm going to draw you a little picture down here. If I had a histogram that was roughly symmetric, right? Where do you expect the median to be? Right in the middle of the picture. Yeah, I expect the mean to be in the middle of the picture. I expect the median to be in the middle of the picture. I would expect the median to be there somewhere, right? Whatever value that is on the x-axis. Now, you do understand to pick up 25% to the left and 25% to the right, since it's roughly symmetric, I need to go about the same distance, right? So I would expect that the first quartile is there somewhere and the third is, what happens when I make that box? Look, that's the box plot on its side, right? So I would expect the median to be somewhere in the middle. That's the reason, if it's roughly symmetric, when I'm looking at the box plot, I expect the median to be somewhere in the middle of Q1 and Q3, equally distant from them, from M. Okay? Now, we go to the other two shapes that we like to talk about here. Skewed right I'm going to give it to you like this. The median is closer to the first quartile. Or if you like, the third quartile is further away. Okay? So if I'm looking at a histogram, just to show you why this works like this, why we would expect this, if I'm looking at a histogram that's skewed to the right, well, again, I would expect the 50-50 point, the median, to be here somewhere. Now, how far do I have to go to the left to pick up? Now, you understand why I'm saying 25, because I know that little red mark, I have 50 to the left and 50% to the right. So if I need to pick up 25 between the median and the first quartile, because remember, there's 25% there, do I have to go very far? No. I got to come out here somewhere for the first quartile. How far do I have to go out to find the third quartile where I have 25% between the median? I got to go out further. So when I look at that little part of the box plot, notice the median is closer to Q1, to the first quartile. All right? What do you think skewed to the left is? It's just the other way, right? So if I'm looking at skewed left, the median is closer to the third quartile. So, if I got something that's skewed to the left, the tail is going to the left. I would expect the median to be here somewhere. I don't have to go as far out to get the third quartile to get 25 and 25 between it and the end. And I got to come further out here. So, you notice the median is closer to the third quartile. And I'm just talking about the box plot, right? You stand it up. The median is closer to the third quartile. I'm expecting a histogram or a stem plot of the data to be skewed to the left. If the median is closer to the first quartile, I'm expecting the distribution of histogram stem plot be skewed to the right. If the median's about in the middle of the box, I'm expecting things to be roughly symmetric. Now, I'm going to take you back to your book here on page 54. There are the two side-by-side box plots of the travel times for New York and North Carolina. Now, the thing I told you on Thursday is people always want to give you these box plots and you want to describe what you see. Well, one of the things I described to you last Thursday is which travel times are more consistent. Which ones show less spread, which ones show less variability. It's the one with the smaller box, right? So the North Carolina travel times are more consistent, less spread, less variability. They're more alike, right? New York has more spread, more variability, and less consistent. Yeah. The other thing I can tell you is the North Carolina times, as far as that little line, the median in the box plot, it's pretty much in the middle there, right? So I expect them to be something that looks like roughly symmetric. What can you tell me about the New York travel times? What would you expect if we made a histogram or a stem plot for them to look like? I'm expecting them to look skewed right because the median is closer to the first quartile than it is to the third. So that was a little part we just talked about there. Now, there's two things left in this chapter. All right? I promised you three things at the beginning of this chapter. A way to calculate the center, a way to calculate the spread, and a formula, a technique for spotting what we want to say is possible outliers instead of just looking at the histogram or the stem plot. Okay? So what we want to do is this. We want to talk a little bit about spotting, picking out possible outliers. What we're going to do is we're going to give you a formula to decide when an observation is too far out the tail, too far away from the rest of the data. Remember, outliers are too far to the right, too large, too far to the left, too small compared to everybody else. That's what, they stand out. Now, we're going to come up with a formula that says how far they have to be from the rest of the data before we start talking about it, instead of just eyeballing. All right? Now, to do this, we need to have a little talk about what's called the Interquartile Range. This is denoted IQR. You'll never hear me say anything other than IQR. It's the interquartile range. That's our notation for it. And the way you calculate this is, it is the third quartile minus the first. It's giving you the range of the middle 50%, right? That is the length of your box in your box plot, Q3 minus Q1. What you're seeing in the box plot, that length there, right? That distance, that is your interquartile range. That is the spread. I'm going to write this down. This is the range of the middle 50%. It's what you're seeing in your box plot. Third quartile minus the first. It's that range. It's that spread. All right? So for any set of data here, if we've got the quartiles, we can calculate this interquartile range. Now, obviously, yeah, I say obviously. It may not be. The larger the interquartile range, the more spread of the middle 50%, right? The larger that number, that's just a number. The interquartile range, that's just a number, right? The larger that number is, the larger the spread of the middle 50%. When you're looking at the box plot, the bigger the box is going to be, right? So the more spread you're seeing in your data, okay? Now, let's do this. Let's take the New York travel times. We did all this work last week on Tuesday and on Thursday. We had the first quartile there is 15. Look, it's in your book. Actually, it's right on page 55. The third quartile is 42.5. Now remember, these are minutes, whatever the units. The interquartile range is, you take the third quartile minus the first. You get 27.5. So in the box plot, the range of that box, the length of that box is 27.5 minutes. Okay? Now, the reason we need the interquartile range, look, it does a couple things for us. One is it tells you about the spread of the middle 50%, right? That range. The range is 27.5. You're telling me about the variability. You're telling me how big that box is. You're telling me how much spread you are seeing. Okay? The other thing is it's used to help spot possible outliers. Now, here's what we're going to do. It's a formula. I'm on page 56. A lot of times, we don't use this a lot, but we need to know this. All right? Page 56. There's something called the 1.5 times IQR rule. Look, here's what we're going to do. All right? Think about it like this. I have a number line. I have all my pieces of data here. I'm going to set what I'm going to call an upper fence and a lower fence, right? And as long as the data stays between there, you're not considered an outlier. But as soon as you jump outside, in other words, you're bigger than the upper fence or you're smaller than the lower fence, you're going to be called a possible outlier, right? We need to start looking at you. So we're setting two fences, two places on this number line. If you're too big or if you're too small, you'll be an outlier, right? You'll be a possible outlier. So here's the way it goes. The reason it's called the 1.5 IQR rule is because the upper fence, okay, this value we're going to set, we're going to take the third quartile, right? Remember, that's the one that has 75 and 25. We're going to add to that 1.5 times the interquartile range. So, you've got your first quartile, you've got your third, you've got this interquartile range here, right? The spread of the middle 50%. You're going to take 1.5 times that, 1.5. Now, if you're past that point, you're too far away from the middle 50%. You're a possible outlier at that point. All right? The lower fence gets set.
Switched over to Wi-Fi phone to make sure.
Oh, I surely didn't make the little boy cry. Maybe I did. The lower fence, right? So it's the 1.5 times IQR rule. You're going to subtract the 1.5 times IQR. So if this is your first quartile, you're going to go 1.5 times that middle 50% spread. And if you're past there, you're a possible outlier. So that's an upper fence and a lower fence. The reason it's one, look, they had to decide on how far out the tail you needed to be. And what turns out to be a good measure of how far you are away, if you're more than 1.5 times the spread of the middle 50% above the third, you're too far out the tail that way. If you're more than 1.5 times the interquartile range, the spread of the middle 50% below the first, you're too small. Right? So we're going both directions here. There's an upper fence and there is a lower fence. Okay? So here's what we're going to do. We're going to look at those New York travel times, and we're going to see if there's any possible outliers in that data set. Remember, we already figured out what the interquartile range was. It was 27.5. Remember, you took the 42.5 minus the 15. That was the range of that box. That was the spread of that box, 27.5. Okay? Now, if I want to set the upper fence, I'm just going to use that. I'm going to take, that's your third quartile, right? Plus 1.5 times 27.5. Right? So, I mean, you can do the 1.5 times 27.5 separate, and then you're going to add that to 42.5. And when you do that, you get 42.5 plus 41.5, which is 83. It's 25 here. Sorry, this is 41.25. You're going to get 83.75. So if we see a value in the data set that is greater than 83.75, you're looking at an outlier there. Now, you always got to do, I always do both, just to be safe for you. The lower fence, remember, you're going to start with the first quartile, 15, minus that 1.5 times 27.5. And when you do that, you're going to get 15 minus 41.25, which gives me a minus 26.75, I think. Am I close? I'm close. 2.5? Now, what we've done is we've set 2 points, minus 26.25 and 83.75. Are we going to have any travel times to work that is smaller than minus 26.25? Travel times works positive, right? So you don't have to worry about anybody on the low end. Do we have anybody above 83.75? Yeah. In your data set, the largest value, 85, is a possible outlier because it is greater than 83.75. It's larger than the upper fence. It jumped over it. It's a possible outlier now.
So you would do this if you just had your forward numbers, or 5 numbers.
Oh, so the question comes up, the problems are going to ask you, right? All of a sudden you're looking, so where everything starts is you look at a histogram or a stem plot. And you say, well, you know, it looks like I got somebody stuck out in the tail. So you're going to need what? You're going to need, you need the Q1 and Q3, right? Because then from that I can get the interquartile range, then I can set the upper fence and the lower fence, and I can start telling you if you got possible outliers. Yeah. I mean, it's possible that you're looking at the data and things are still roughly symmetric, and you may not have the quartiles, right? But you're going to need them to use that rule because that's what's involved here. Okay?
That's
So,
what I was confused
Yeah. No. So we might have the 5-number summary to start with. Normally, if we start seeing outliers in the data, remember the mean don't behave well with outliers, right? So we immediately want to go to the 5-number summary. We got it. We can figure. Okay. So I'm going to back up here one moment. I'm going to put a little star on that. This is how you set the upper fence. This is how you set the lower fence. You need the first quartile and you need the third. From there, you can get the interquartile range. And then from there, you can start adding to the third and subtracting from the first. Okay? Now, that was the one we did there. Okay? Now, before I do this last little part here about, look, I'm on page 57, and there's one more measure of the spread, measure of the variability, and it's called the standard deviation. Look, here's the thing. Remember you got the mean and you got the median, right? How did we measure the spread or variability with the median? That was the quartiles. That was the 5-number summary, yes? I need a measure of spread or variability that goes with the mean. That's the standard deviation. Before we do that, what I would like to do is I'd like to come over to a homework problem, and I want to scream at you a little more about box plots, 5-number summaries. How do I want to use a box plot? Okay, so I'm coming over here, and the problem I'm on page 71 here, okay? And I would like to look at problem 2.47. I mean, I never did show you how to make a box plot in Minitab. I'd like to show you that. I'd like to show you when the problem doesn't tell me, we got to pay attention to what it's asking for, how we're going to handle it, right? So in this 2.47 on page 71, it says good weather and tipping. Favorable weather has been shown to be associated with increased tipping. I'm assuming they're talking about in a restaurant, right? They tip more when the weather's good. Will just the belief that future weather will be favorable lead to higher tips? The researchers gave 60 index cards to a waitress at an Italian restaurant in New Jersey. Before delivering the bill to each customer, the waitress randomly selected a card and wrote on the bill the same message that was printed on the index card. 20 of the cards had the message, the weather's supposed to be really good tomorrow. I hope you enjoy the day. Another 20 cards contained the message, the weather's supposed to be not so good tomorrow. I hope you enjoy the day. The remaining 20 cards were blank, indicating that the woman was not supposed to write any message. She just gave him the bill. Okay? It says, choosing a card at random ensures that there was a random assignment of customers to the 3 experimental conditions. There was 3, right? What'd you get on your card? You got a good weather message, a bad weather message, or you got no message? Anybody had an equal chance of getting any one of those 3 types of cards. It says, now here's the punchline. Here are the tip percents for the 3 messages. It's on the bottom of the page. There's a table, right? They have the tip percentage for good weather, bad weather, no weather. I got to flip the page. Compare the 3 distributions. How did the tip percent vary with the weather report information? So in this problem, 2.47, yes, it's long-winded. Okay? What do you have measured on these different weather reports? You have the tip percent, yes? So you have the quantitative variable, measured on 3 Now look, I just took all the stuff out of the problem. I'm just telling you, what I'm looking at is this idea of the tip percent, that's a quantitative variable. How many groups do I have it measured on? I got it measured on 3 groups, right? The good weather group, the bad weather group, and the no weather group. And the problem says compare the 3 distributions. There are 3 distributions here. There's a distribution of tip percent for each one of the types of weather that they said. Good weather, bad weather, no weather. This is screaming for side by side box plots. if you go back and look at your notes from last Thursday where I talked to you about box plots, I told you the best use of a box plot is to do side by side, where you have the same quantitative variable measured on two or more groups. This is what this is calling for. This is what this is screaming for. You have tip percentage measured on when the good weather was told, the bad weather was told, and the no weather is told. And you want to know if there's any difference between the tip percent between those three groups. You want side-by-side box plots. Okay? So, I'm not going to sit here and find the 5-number summary for each one of these groups and make a box plot and do this by hand. Okay? So what we're going to do is we're going to come over here. We're going to find that file. And I'm assuming that file, right, it's named right there. And I'm assuming it's called tipping in Chapter 2. Is that what it's called? Now look, you've got a column here that gives you the different weather, right? Good, bad, no weather, and that's just the percent in the next column. Yeah? That's the exact same thing here, except they just stuck it all together. The first column is telling you the type of weather. The first column is telling you the groups. And the second column is telling you the different values of your quantitative variable here. Yep. So if I want to make side-by-side box plots, I go to Graph, Box Plot. Now, you see the one that shows up there in the upper left-hand corner? If you just have a single group and a variable, hell, you can just make a single old box plot by itself, right? Like the first one I showed you last Thursday. Or, if you have groups, we want to choose this one. Okay? It says, where's the graph variable? It's asking you, which column is the quantitative variable in, right? That's what you're trying to graph, is the 5-number summary of that. There. And then it wants to know, okay, where are the labels for the different groups that you have? That is the weather. Okay? One more time. The graph variable is what column the quantitative variable in. When it asks you for where are the groups, what's the categorical variables for grouping, there's a column there, right? Where are the labels? Where are the categories? Okay? We click OK. Oh, that's the reason we don't do this shit by hand. We'd still be working on the 5-number summary for the good group. Right? Everybody understand? Now, is anybody shocked here, right? There's 3 groups. There's a 5-number, there's a box plot for bad weather, there's a box plot for good weather, there's a box plot for no weather. Yeah? Yeah? If you want to know, we didn't actually do the work here, right? We didn't calculate anything. I just put my cursor on the box. Is the 5-number summary looking at you? Yeah, there's the first, there's the median, there's the third, there's the interquartile range. Hell, it gave you IQR also. The whiskers, that's the maximum and the minimum. Yeah? Sample size. How many people was in your group, right? That N, remember N, that's how many individuals you have? There must have been 20 in that group. Okay? Over here, 5-number summary. There must have been 20 people in that group. So on and so forth. Yes? Now, one other thing to mention here. They don't put the little lines for the minimum maximum wherever they stop. That's it. You see the little stars, the little asterisks? Minitab's trying to tell you something. Any thoughts what Minitab is trying to tell you? Minitab's trying to tell you, look, I did all this work for you, and I actually checked the 1.5 times IQR rule. You know what I found? The guys I labeled with little stars, those are possible outliers. It's using the rule we just talked about to do this. So if you look at the bad weather, there's 1 high outlier, there's 2 low ones. The good weather didn't have any outliers in it. The no weather had 3 low outliers. Yeah? I still haven't got to the punchline yet. If I look at the distribution for the bad weather, is it roughly symmetric, skewed to the right or skewed to the left? What are you expecting? What's the median closer to? It's closer to the third. I'm expecting it to be skewed to the left. Look at the one about good weather. You notice the median is a little bit closer to Q3, right? If you told me that one was roughly symmetric, I wouldn't be upset. If you told me it was skewed to the left, I wouldn't be upset. What about the one with no weather? They all looking like a little skewed to the left here, aren't they? Yeah. Let me ask you this, because the punchline is this. what was written on the check make any difference? Okay. If I was the waiter and I got to choose what I wanted to write, sure as shit I'd be writing, you're going to get good weather tomorrow. Does anybody understand why? You know what the thing I wouldn't write on the check is? Bad weather. If I didn't have a pen, I just wouldn't go look for one. I'd just leave the shit blank. Because which ones actually had higher tips? It's the one that's higher up on the picture, right? The good weather. Yeah, when you told them good weather, they had a higher percent tip. What about the no weather? Hell, that's the next one. What about the bad weather? That's the lowest. So the one thing you don't want to write on the check is you're going to have bad weather tomorrow. So did it make a difference what group they got, what group we're looking at? And the answer is, yeah, these distributions are different. Yeah? Generally, the good weather produced a higher percent. Bad weather produced worse than no weather. Which one of these three are showing the most spread, the most variability? Which one has the largest interquartile range? I'm giving you three things that are all the same. Which one are showing the most spread, the most variability, the largest interquartile range, the biggest box? Good weather. Which one is showing the least amount of spread, the smallest variability, the smallest interquartile range, the most consistent? No weather. Am I talking about how big they are? So when you're just looking at box plots like this, there's two things you always want to mention. Well, there's three now. You can tell me a little bit about the shape of each one of them based on where the median is, right? We talked about that. You can tell me how much spread you're seeing in the data by how big the box is comparing to the other ones. Yep. And then if one of them is bigger than the rest of them, right, then that was the one that had the best. Then the next one was no weather, good weather, no weather, and bad weather. And I told you a little bit about the outliers. That's what Minitab is doing for you. That's how you attack a problem like that. As soon as you see that I got the same quantitative variable measured on two or more groups, in this case 3, what do you want to make? What do I want to look at? I want to look at... Now, I left off the obvious thoughts at this point because I'm going to assume that you can see that the first quartile of the good weather is greater than the third quartile of no weather or bad weather. Everybody agree with that? Remember, it always goes first, median, third. The first quartile of the good weather is greater than the third quartile of the other two. Yeah? Yeah? Things like that. There's 7,000 things I could ask you at that point about looking at this. I mean, I could ask you, what the hell's the median value for good weather? I don't know. It looks around 22, don't it? 22, 23? I mean, if you want, I get a little piece of paper and put on there and go straight across. 22, 23. What's the first quartile of no weather? I don't know. It looks maybe like 19 or something, right? Can I read where the lines are? Remember, ignoring the minimum, the maximum, and all maybe possible outliers, it goes first quartile, median, third quartile. That's it. Right? So that's what 2.47, that's how you attack one of these. You attack 2.46 the same way. And there was some crazy one about surgical skills and video games back here on page 248. It's the same thing. You've got a quantitative variable measured on two or more groups. How do you compare that quantitative variable for this group, this group, this group? I don't care. There could be 2, 3, 4, 5. I don't know. How do you compare? There. Okay? Now, while we're here, I'm going to leave that tipping file up. I want to show you something. Look, you need to be able to calculate the median with a calculator on a test. You know, if I give you like 10 or 12, put them in, add them up, divide by the total. You need to be able to calculate the median by hand. Quartiles by hand. In other words, you need to be able to calculate the median, the mean, and the 5-number summary by hand for a small set of data. I mean, I'm not going to give you 300 pieces of data and ask you to do that. With that said, if you go to STAT, basic statistics, in case you don't know, when you start telling me about center and spread, mean, 5-number summary, you are telling me about descriptive statistics. You are describing the center and spread. So if I choose display descriptive statistics, if you want to ignore what kind of weather you had, we could do that. But I'm going to actually give you the 5-number summary and everything for each one of the groups. They want to know, where's your variable? Where's the quantitative variable? That's the percent. By variable. In other words, I want to do for the good weather, the bad weather, no weather. The N is how many individuals you had. Ignore the N star. The mean of each one of them is given to you. Ignore SE of the mean and standard deviation for a second. You got the minimum, the first quartile, the median, the third quartile, and the maximum. We got the 5-number summary for each one of the groups. Okay? It's that easy to get those. Where'd I go? One more time. Stat, basic statistics, display descriptive statistics. If I didn't care about the groupings, and I just wanted to do all 60 of those tip percents, I wouldn't have put anything in where it says by variable. And it just gave me the 5-number summary and all that stuff just for all of them together. Okay? I'm sorry I used the software so much. We just saved ourselves about an hour. Between making the box plot for us and then doing the 5-number summaries and all that stuff for us, it saved us about an hour. At least. Okay? Any questions, Johnson City? Streamers? Look, I always like to, look, I went to a long way at the end of the homework to get that problem about tipping. Because, okay, so what's the actual use of a box plot? Well, that's it. Then I want to read problems where nobody tells you what to do. I mean, if you've been doing homework problems out of Chapter 1, or even the beginning problems out of Chapter 2, they always tell you what to do, right? Oh, make a histogram. Tell me about the shape, center, spread, and possible outliers. Or at the beginning of Chapter 2, calculate the mean, or calculate the median. Calculate the 5-number summary, right? They're always telling you. When you get further along at the end of the chapters, they don't tell you. You know the problem I gave you for homework for Thursday, the one about the histogram? It says describe the distribution. You got to know. That means tell me about the shape, the center, the spread, and outliers. That problem right there, they never told you to use side-by-side box plots or make the 5-number summaries. They said, here, I've got 3 groups with a quantitative variable measured on them, and you have to decide on how to attack. How do you compare? I'm telling you that. You compare with side-by-side box plots. Okay? So, to me, the last calculation in this chapter is this idea of measuring spread. Now, the other day I wrote variability, right? How does your data change from one individual to the next? How are you going to measure spread? Okay? Well, our second one is the standard deviation. Okay. Now, the standard deviation, it's on page 57. There's a box there. Okay. Now, here's the warning. All right. 5-number summaries in this hand. The mean and standard deviation in this hand. The mean and standard deviation always go together. The 5 numbers and the 5-number summary always go together. Nothing comes from over here that goes over here. Nothing from here goes over there. It's always mean and standard deviation or the 5-number summary. Okay. Always. Now, I got to write that for you even though I said that to you. You use the mean to measure center. And the standard deviation. Can I do that to you? All right, standard deviation to measure spread. They go together. Can I scream at you one more time about that shit? The mean and standard deviation stay together. The mean is used to measure the center. The standard deviation is used to measure the spread. The 5-number summary stays together. Remember, the median measures the center. The first and third quartile mark out the middle 50%. Interquartile range now, minimum, maximum gives you the extremes, right? Nothing switches here. Those two go together all the time. Now, I'm going to, look, if you're reading that box gets ugly in a hurry. All right, so I'm going to kind of give it to you in how I think about the standard deviation. And the standard deviation, and I haven't given you any notation, I haven't given you the formula. The standard deviation measures how far the observations, remember that's my observations, are from their mean on average. So I'm going to go back and forth between this. Remember, the quartiles chop the data up into 25, 25, 25, 75, 75, 25, the median, 25, 25, 25. The quartiles measure the spread of the middle 50% by giving you an interquartile range or a number there, right? So, you know I'm bad about talking with my hands. So when you hear me talk about standard deviation, my number line is still sitting here, right? Here sits your mean. The standard deviation measures the spread about the mean this way. The larger the standard deviation, the more spread you're seeing, right? The smaller the standard deviation, the less spread you're seeing. Okay? Standard deviation measures how far the observations are from their mean, being the center, on average, right? It's giving you a number. It's telling you on average, this is how far the observations are away. You know, they're 100 away or 200 away. Obviously, there's some further and there's some less, right? But the larger that number is, the more spread you're seeing about the mean, both directions here. Okay? Now, here's the thing. Page 57, box. Okay? It says the variance. So there's a starting point to getting us to the standard deviation. And the variance, look, I'm not going to write up all those words they have there. The variance is always denoted S squared. When you see that in our book, they're talking to you this idea about the variance. And it says the variance denoted S squared of a set of observations, so you've got some set of observations, is an average of the squares of the deviations of the observations from their mean. Now look, I can read that shit there 4 or 5 times. It don't get no better. The variance, okay, is measuring how far, when you square everything, they are away from the center, being the mean. Okay? The larger the variance, the more spread you're seeing. Right? The more spread out things are about the mean. The smaller it is, the closer they are to the mean. Okay? Now, they give you a formula here for the variance. I'm going to write it down. Now, remember, you have n observations here. Right? There's n pieces of data. There's n individuals. They give me 1 over n minus 1. So you're dividing here, right? We're taking an average. Yes? Normally when you take the average, you divide by all of them. Here you're dividing by one less than all of them. We're going to have that talk in a moment. And then before you do that, you add a bunch of things together. You take each observation. Remember, I did that to you with the mean, right? The little subscript is telling me we're going from 1 through n. You're going to subtract off the mean, and you're going to square them. Okay? That's the formula for the variance. We ain't never going to use that formula. Maybe once. Now, to get from the variance to the standard deviation, the standard deviation is denoted just by a little s. Well, how would you go from s squared to s? You would take the square root. That's probably the second worst formula we see. And when I say worst, there's just a lot of crap going on. All right, there's a lot going on there. Now, I want to point something out to you because I keep telling you that the standard deviation is this average, how far the observations are from their center on average, right? So I'm going to break this formula down for you like it works in my head. If you see this part right here, all you're doing is you've got your number line and you're taking the mean, and then for each observation you are subtracting the mean from it. That's all you're doing, right? So you got all the observations, and you're going to subtract the mean from each of the observations. Does everybody understand that some of those will be positive and some of those will be negative? If I'm on the number line and here sits my mean, and I have an observation over here, and I subtract that, the mean from that, you understand that distance there is going to be negative, right? If an observation is smaller than the mean, that number is going to be negative, yeah? If an observation is larger than the mean and I subtract, that distance there is going to be positive. So some of these are going to be positive if the observation is greater than the mean. Some of these are going to be negative if the observation is less than the mean, yeah? Okay, so math people hate that kind of stuff. We hate shit like that when we do a subtraction, and some of them are positive and some of them are negative. So how's a math person fix that? The hell, we square them and make them all positive. Right? That's what a math guy does. You got positives and negatives, I want them all positive, just square them all. Now, you understand that if that, take an observation and subtract the mean, that's a distance, yeah? When I square them, is that still a distance? No, hell, that's a positive distance. It might be a little bit bigger, but it's still a distance, right? So all that stuff I have there in red and blue, that's just giving me some idea of a positive distance that each observation is from the mean, right? What's the little sigma tell me to do? Add all them positive numbers together, right? So now I have this sum, right? It's added up all those positive distances from the mean that the observations are, yeah? When I divide by n minus 1, what am I doing? I'm taking an average, yes? I know, it should be n. There's a reason why it's n minus 1. We're dividing by n minus 1 because we're taking an average. And then what's the hell is the square root doing? Well, no, we had to square all the stuff to make them positive, so at the end we're going to take the square root to undo that, right? So now we're back to a particular number here. That's exactly what's going on. I mean, I know the formula is ugly. That's all we're doing. The reason I went through that is because I just want to get it stuck in your head that the standard deviation is measuring how far an observation is from the mean on average. It's an average. That's what it is. The reason I want you to think about it like that is because what I want to get in your head is the smaller that number is, well, if I got things on the number line, the closer the observations are to their mean. The larger that number is, the more spread out things are, right? So the larger the standard deviation, the more spread, the more variability. The smaller the standard deviation, the less spread, the less variability, right? You're measuring spread this way, about your mean, okay? Now, I got one more word to write on this page. Oh, no, you think I'm nuts. I'm right underneath that box. In practice, use your software or calculator to obtain the standard deviation from data. The dude knows. You ain't going to do this by hand. I mean, I'm going to show you a little bit with maybe 6 or 7 pieces. If you got 20 or 30, you ain't doing this. There ain't no way. So here's the thing. I'm going to make you a promise. Okay? If you need to calculate the standard deviation, you will have access to Minitab. In other words, in a homework or something like that. On a test, if I want you to know about the standard deviation, I will give it to you. It'll already be calculated for you. Right? So anytime that you would have had to calculate it, you will have the software. You'll have Minitab available to you. Okay? Now, I want to look at this example 2.7 here. It's there. It's a small set of data to show you what would have to happen here if we were going to do this by hand. So, this example 2.7, all right, it says Georgia Southern University had 3,219 students with regular admission in its freshman class of 2013. For each student, data are available on their SAT, ACT scores if taken, high school GPA, and the college within the university to which they were admitted. In exercise 3.9 on page 98, the full data set is there. Well, I'm not in chapter 3 yet, so I'm not going to worry about that shit. Mathematics scores will be examined. Here are the first 5 observations from the data. So here's what you got. You've got 5 students. And we might as well get used to it. Hell, that's your little n. I use little n in the classroom. Minitab uses a capital N. That's how many is in your data set. How many are we looking at? All right, how many individuals? They've got 490, 580, 450, 570, 650. I'm going to write them like this. I've got 490, 580, 450, 570, and 650. Now, I'm going to put a little line there. These are your little, those are your observations, right? Now, for me to do anything here, I have to have the mean. How would you find the mean of those 5 math scores? Would we add them up and divide by 5? Yeah? So if you add these up and you divide by 5, I'm not going to do that for you. You're going to get an X bar of, the book tells me it's 548. Okay? So the next thing we would have to do is, we would have to look at, remember the part I had underlined in red there? You got to look at each observation minus the mean. I need to look at this part. Each observation minus the mean. Yeah, I know the book calls these deviations. Hence, standard deviation. It's the distance, right? It's actually going to come out plus or minus. So if I take 490 minus 548, what do I get? Minus 58? Right? Because remember, I'm taking the observation and subtracting the mean. I get minus 58. If I take 580 minus 548, I get 32. If I take 450 minus 548, I'm going to get a minus 98. If I take 570 minus 548, I'm going to get 22. And if I take 650 minus 548, I'm going to get 102. What's wrong?
How did you get that first one?
I took 490 minus 548. That's not a minus 58? Oh, it's got to be. I'm cheating. It's my,
Put 580.
Yeah.
I put it in there.
So there's your deviations, right? That's the distance from the mean to each one of the observations. Remember, some are negative and some are positive, right? If the observation was smaller, it's negative. If the observation is greater, it's positive. Okay? Now, one little thing. If we were actually doing a lot of these by hand, our little check would be, we would add that column up and we would get 0. That was your check to make sure you didn't screw that shit up. Now, that's not special to this problem. That happens every time. If you take the observations and subtract their means, and you take all those pluses and minus numbers and you add them together, you always get 0. Right? So what this is saying is the sum of the deviations, the sum of those distances is 0. Wait, does that make sense? The mean's the average. Shouldn't the observations on this far to the right be the same as the ones this far to the left when they're all put together? That's what the hell makes it the mean, right? It's in the middle. Shouldn't be a great shocker when you sit there and think about it. Now, the next column is, I'm working through the formula, right? That was those differences there. And now we're going to square these, right? You're going to take each one of those values that you subtracted, and you're going to square them, right? These are your squared deviations. So you take a minus 58 and square it. It's going to come out positive. I'm going to look here in the book, and I'm going to get 3,364. If I square 32, I'm going to get 1,024. If I square minus 98, I'm going to get 9,604. If I take the 22 and square it, I get 484. If I take the 102 and square it, I get 10,404. Don't be shocked, they're all positive, right? We squared them all. We add that column together. You add that column together and you're going to get what do I got here? 24,880. Okay? So that's the summation. That's that part over here. We haven't divided by anything yet. We haven't taken the average. Look, that's just the total distance, squared distance that these are from their center, from their mean. Okay? So if I want the variance at this point, remember, this is, you see that, we're talking about variance. Okay? You're going to take 24,880, and you're going to divide by 4. Does everybody know why we're dividing by 4? It's always one less than the number of observations you're working with. You're working with 5 here. We're going to divide by 4. And when we do that, we're going to get 6220. That's the variance. Look, we like the standard deviation in this class. Sometimes we'll ask you some questions about the variance, but the standard deviation is our measure that goes along, especially in this class because all the units and everything will work out correctly. The standard deviation, you find it by taking the square root of that number. When you take the square root of 6220, you're going to get, what we got here, 78. So what this is telling me is, I know the mean is 548, right? We calculated that. The standard deviation is 78.87. So on average, how far are the observations away from the center? 78.87. Are any of them exactly 78.87? No, but on the average, how far are they away? 78.87. Yes? That's what the standard deviation is giving you. It's giving you this idea of the average distance that the observations are from their mean, right? So on the average, they're 78.87 points from 548. I'm not going to get crazy with the standard deviation at this point, but what I would like for you to know at this point, if that standard deviation had been 22.31, which one would look like the observations are closer, the 23.21 or the 78.87? The 23 point everything is the observations are closer on average, right? 78, they are further away. Suppose it had been 127.4. The 127.4 is even more spread, right? That's what it's measuring here. See, I can't tell you at this point, looking at this, my mean is 548. 78.87. Is that a lot of spread? I don't even want to think about it yet. I just want you to know the smaller that number is, the less spread you're seeing. The larger that number is, the more spread you are seeing. Okay? Now, I got a couple thoughts here. One of them is, normally when you take an average, you divide by the total number of things. We didn't do that here. Notice, and I'm going to make this a little note. I don't do that too often. We divide by n minus 1 instead of what you would think if I'm talking about an average. Normally you divide by the total number of things that you added together, not one less. We didn't do that here. Now, here's the thing. Okay? I pointed out to you at that second column in that table, they added to 0, right? So what I was pointing out to you is this. When I looked at those deviations, where I subtracted the mean and some of them were positive and some of them were negative, it was 0. And I told you that's always the case. Not special to this problem. Everybody agree, right? Not special. That always works like that. Now, hang on to that thought for 1 second. I'm going to ask you a question. If I have 4 numbers, just 4 numbers, and I tell you they add to 0, and if I give you the first 3, can you tell me the fourth one? That's not a trick question. I got 4 numbers that add to 0. And if I give you the first 3, can you tell me what the fourth one is? The fourth one's whatever makes the first 3 add to 0, right? So if I had 4 numbers and they added to 0, you only have choices for the first 3, and then the fourth one is determined for you, right? You don't have a choice of this one. If these 4 are going to add to 0, and you choose that one, and that one, you ain't got no choice for that one. It's got to make these 3 here add to 0, right? That's what's going on here, right? If we know n minus 1, then the last one is determined for us. No choice. It has to be whatever makes the other ones add to 0. Okay? Now, again, I don't want to get too crazy here, but it's that I got 4 numbers. I could have 22 numbers and they add to 0. Once you get to choose the first 21, the 22nd one is, the last one is determined for you. That's what I'm telling you here. So you only get to choose the first, I'm going to put a number to it. If you got 4, you only get to choose the first 3, right, freely. You have a choice in those, right? The fourth one is determined for you. So what we say is, in this case, the n minus 1, that we divide by, the ones we get to choose freely when we're adding the 0, is called the degrees of freedom. Now, I'm sure you've been in classes where somebody's talked to you about the standard deviation. Hell, you could have been in classes where they made you calculate the standard deviation for like 20 pieces of data. The standard deviation, that little s, always comes with this idea of degrees of freedom. And it's denoted by degrees of freedom. Is always equal to n minus 1, where n is the number of observations. That always comes, for us, that always comes attached. When we talk about standard deviation, it always comes attached with it this idea of degrees of freedom, this df. And it's always 1 less than the number of observations that you are looking at. In this case here, we were looking at 5. The degrees of freedom is 4. If you were looking at 50 pieces of data and finding the standard deviation, the degrees of freedom would be 49. Now, I'm also honest with you that this is not going to play a role at the moment here. All I wanted you to know is the larger the standard deviation, the more spread. This plays a role at the end of the semester. I'm thinking it's chapter... They changed the book on me. I think it's chapter 16, 17, or something like that. It's chapter 18. When we get to chapter 18, I'll remind you that the standard deviation comes with this ideas of degrees of freedom, right? I'll remind you of this little talk. At the moment, I just want you to know that it's always attached. Even though we may not mention it, the degrees of freedom is attached to the standard deviation. It's always 1 less than the number of observations. That's the reason you do that crazy thing where you don't divide by all of them. You divide by 1 less. All right? Now, the other thing I'd like to do is this. Since I'm never going to calculate this again by hand, and you're not either, because remember when I showed you this here, where I went to stat, basic statistics, display descriptive? You see where it says the mean, that's the mean. Ignore that SE mean. We don't need that yet. That shows up in chapter 18 also. You see where it says ST, DVE? That's your standard deviation. All right? So it will calculate it for you. All right? You give it the data, it'll calculate the standard deviation. Okay? I want to give you some facts. The facts to me are more important to what's going on with us than standing here and calculating it. So my facts go like this. The first one is S measures spread about the mean X bar. The reason I put that one like that is because I want you to know that when you use the mean to measure the center, you use the standard deviation to measure the spread about that mean. 2, the standard deviation is bigger than or equal to 0. If somebody tells you they calculated the standard deviation of minus 42.7, that ain't happening. You can't have a negative standard deviation. Remember, it came from the square root. You only get positive numbers out of there. The only time that S is equal to 0. Well, let me ask you this. How would you get a standard deviation of 0? That would mean no spread. All observations have the same value. That's the only way you get a standard deviation of 0. You're looking at your data set. You've got this quantitative variable, and they're all the same value. There are 0 spread, 0 standard deviation. If they're not all the same, the standard deviation is going to be positive. The larger it is, the more spread about the mean. The smaller it is, the smaller the spread. The reason we like it in this beginning introductory class is S has the same units as the original observations. You know, the data that's given to you. If it's measured in inches, standard deviation is measured in inches. If it's measured in minutes, the standard deviation is measured in minutes. Whatever the units are on your variable, the standard deviation has the exact same units. The reason we don't like the variance in this class, I mean, they're both got the same idea, right? They're both measuring spread variability around the mean. The reason we don't like the variance is because the units on the variance are squared. Remember, there's no square root in that variance formula. The reason we like the standard deviation is the exact same units. 4. F is not a resistant measure of the spread. Now, going back to last week, that means that the standard deviation will be influenced by skewness and or outliers. What do you think an outlier, right? Suppose you got, forget any kind of skewness. Suppose you got like something that's roughly symmetric and you got an outlier. What is that going to do to your standard deviation? Is it going to make it smaller or bigger than it should be? It's going to make it bigger. You're going to see more spread than you should have if that outlier wasn't in there. What do you think the tail and the skewness does? It makes it bigger than it should be, right? Because the tail is stretched out there. It's showing more spread than you should see, right? Without the tail. Last thing in this chapter, all right? I'm going to do it like this. I've been mentioning it. Now we're going to write it down. I'm wanting to talk about choosing measures of center and spread. You have two choices. You've got the 5-number summary. Remember, that's the minimum, first quartile, median, third quartile, maximum. Or you have the mean, and standard deviation, which is your X bar and your, okay? That's what we've worked on here in Chapter 2, the 5-number summary or the mean and standard deviations. You want the 5-number summary, the minimum, first quartile, maximum, third quartile, excuse me, the median, third quartile, maximum, if you have skewness and or outliers. Remember, they're resistant to that. They're not influenced very much by skewness and or outliers. When does the mean and standard deviation work the best? Roughly symmetric. No outliers. How do I know if it's skewed to the left, skewed to the right, roughly symmetric, or do I see possible outliers? What do I do first? Always plot your data first. Remember, we're looking at a quantitative variable. What's your two choices? A histogram or a stem plot. Make the graph. Look at it. You see skewness? You want to use the 5-number summary. You see any kind of outliers? You want to use that. You see roughly symmetric and no outliers? You're looking at the mean for the center and the standard deviation for the spread. Now, here's the thing. So that right there was on page 59. Now, on pages 61 and 62, 63, here's the warning. And the warning on page 61 is we're going to be using some technology here, right, to calculate standard deviation and stuff like that. Do not freak out if you've done the quartiles by hand and Minitab gives you a slightly different answer. Right? It can be off just a tad. It won't be off enough to make any difference, but it would be off a little bit. Remember the little... Do you remember when we was finding the median and the quartiles, and if you were between two of them, that we took the one, we went right in the middle, we took the average of the two on either side? Minitab doesn't quite do it like that. So if you're falling between, don't freak out that it might be a little different than what you're getting by hand. Remember, on the test, you're going to get graded by what you do by hand. So that's the warning with that. And the other thing at the end of this chapter is organizing a statistical problem. Look, it's a 4-step process. I'm going to be honest with you. Solving any math problem, it don't have to be in this class, is always a 4-step process. This guy wrote it like there's some magic here. There ain't no magic here. You give me any math problem, it's a 4-step process. And the process is on page 63. It says, state, what is the practical question in the context of the real-world setting? What the hell are you trying to answer? All right, what is the question? What are we talking about here? Plan. What specific statistical operations do this problem call for? What do you want to do? You want to make a box plot? Do you want to make side-by-side box plots? What, you want to calculate make a histogram stem plot? What? Bar graph? What do you want to make? Solve. Make the graphs and carry out the calculations needed for the problem. Oh, so I was looking at a quantitative variable in 2 or more groups, and I wanted to make side-by-side box plots? We made it, right? That's what you would do. Conclude. Give your practical conclusions in the setting of the real-world problem. Remember when I told you that the good weather gave a higher tip percent? We answered the question. There's always 4 steps. State, what the hell are you trying to do? Plan, how am I going to attack that problem? 3, well, whatever in the hell you decided to do in the plan, right? That's what you're going to actually do and solve. And then you got to interpret in the end, you got to actually answer the question that was asked to you. Okay? The only reason I point that out to you is I don't give that to you. A lot of the problems in the book do. Okay. I'm interested. Do you know what you're doing? Right? Can you attack this problem? Now, that brings us to the end of chapter 2. And we're about ready for chapter 3. All right? what I was thinking was this. Okay? Is in chapter 3. I didn't mention this when I started chapter 1, but the first 3 chapters go together. All 3 of the first 3 chapters, you're looking at a set of individuals and you had a single variable measured on them, correct? Whether it was categorical or quantitative. In chapter 1, we made graphs. If it was categorical, you made a bar graph. Sometimes you can make a pie chart, right? Or you made a histogram and a stem plot if it was quantitative. Then we went to chapter 2. What did we do? We added calculations to the histogram or stem plot for a quantitative variable. Center and spread. Center and spread. Then I gave you a little formula about finding outliers, right? Now, chapter 3 is the final step when you have a group of individuals and you have a single quantitative variable measured. Right? So chapter 3, the title of it is... Now, I noticed all of us haven't been bringing a calculator. We're going to want a calculator come Thursday. It's going to turn and look like a math class at that point, after I get you started. Okay? To me, it hasn't looked a lot like a math class. It seems like I do a little bit of calculation. Sometimes I use the software, and then we talk a lot about what we found, right? We explain it in the context of the problem. Chapter 3 is a little different. It's going to turn into looking like a math class at that point. We're going to do some calculations, some formulas we need to do, and stuff like that. So, here's what I got. The title of this is normal distribution. Do you remember what a distribution is? It always tells you 2 things about your variable. It tells you what values the variable can take, and it tells you how often it takes those values, right? That's the definition. I don't know what that word normal means. I'm assuming we're going to find that out on Thursday. But when we're exploring a distribution, I'm going to summarize what I just told you. So we're exploring a distribution. We're interpreting a histogram. Now, what we have is we have one quantitative variable. There's nothing interesting about a categorical variable at this point. That was all done in chapter 1. Step 1, I'm going to give you some steps here. We always plot the data. I just told you had 2 choices, either a histogram or a stem plot. 2, you tell me about shape, center, spread, outliers. Now, I'm going to put this number 3, but you give me numerical summaries. I can't do that. Calculate. Center. Spread. And when you look at the data, if you think you see outliers, so I'm going to put it here. 1.5 times the IQR rule. If you don't see anything, don't do it. Right? But if you see something, check it. Right? If something looks suspicious, check it. Okay? That's what we've done up till now. Plot your data, histogram, stem plot, shape, center, and spread. That was chapter 1. Calculate center and spread, 1.5 times IQR rule. That was chapter 2. So there's a 4th one here, and then we'll go home. Number 4. The overall pattern, that shape you see is so nice, right? So the overall pattern that we are seeing is so regular, so nice, so visible. We can describe it by a smooth So what we're going to do on Thursday is we're going to look at a histogram, and the pattern is so nice that we can draw in a nice smooth curve that tells us everything we wanted to know about that histogram, right? We're going to describe what we've been doing with a histogram, and we're going to trade that for a smooth curve that can be drawn in. Okay? Y'all be careful going to the house. Don't forget my homework problems for Thursday. Be careful.